Fine. Already we have Dr. Balapan sir here and Dr. Mankito sir from IIT. They're all here and we're waiting for our director sir to start the session. Yeah, me too. Yeah, boss. Sanjay Singh from Papa. Good morning and greetings from my myself, P. Ramalingu, from Department of Concept Analysis and Typological. I extend this to welcome our respected Director, Typological, and respected person, Dr. Nandu from IIT Bombay, Dr. K. Malagapai, and Dr. Sarma from Thermo Scientific, India. This Monday online seminar on LC-HRMS in drug design and development. To the preface of the event, I wish to inform you that our NIPE will introduce two new departments, that is pharmaceutical analysis and science, in addition to the existing three departments, that is pharmacy practice, biotechnology, and pharmacology and toxicology. As a part of this facility, we have installed LC-HRMS with our campus. Now it's under utility for our students research. In this context, as our directors are suggestions, and you are enlightening the public on the application of LC-HRMS in the design and development, and we have planned this event, and this event is comprised of four sessions. Two sessions in the morning and two sessions in the evening. The first session will be by Superman sir. For lunch, we have Dr. Saran, and followed by student interaction with Saran Kumar for integrated research. With this, without further delay, I request our director sir deliver the open remark on this event. Sir, may I request? Very good morning, very good. Organizing the party of Congress. It's a wonderful morning. We have assembled here. Drug design and development, how LCMS what ability. The very important to note that the Ramali and the archiving committee, Dr. Murali Kumarasamy, we both state what Sir P. Aishwarya, Mandal, Ethan, Samir, and Dr. Shimurti are together. They do to happen to understand the drug design development. You all know that how it is very important the data for developing drug development. HRMS facility, it was one of the leading Raipur. I can say that at the NTR Raipur, the Raipur Hajipur, they elected to the facility part. Then later on, others also the contact facility. The proteins are very important. Recording. Specifically, these DNA to RNA are the proteins and then
What we providing the ability to over the years, top are develop the topic, how that is the vehicle insight into vehicle design. The biophysical area, the non-physical is one of the prominent area, the data, the same the proteomics for identification of molecular target. The Balabalan from Agapa University is that is similar to us in the DNA that the proteomics aspect. Actually, the method is a LC-HRMS. The together you can learn very unique understanding of how the HRMS application is a very important facility for utilization of the drug. Utilization for drug design and development. It makes you skillful, improve your employability and your research the skill. With this, you can develop your the drug design and to meet the drug discovery requirement. Either it is the formulation requirement or it is a new molecule or I can see that even this biological or the biophysics, all these aspects, over aspects in different area. You understand if you utilize the skill of the HRMS application, the technique of HRMS application, it will improve writing better. I believe that it will be one of the wonderful time to learn today. It is the people I appreciate the organization community. Dr. Ramli Murali, Dr. Mandal, all the team members who are part of this activity will be very much encourageable and I appreciate the commitment, the role here. And I thank all the speakers and the request and available during the morning session, though it is a Saturday, so everyone is committed and available for the session. It is something to I gave my message for the organization committee and welcoming all the speakers for their the presence over here and the participants to utilize the time in very rational manner attention. This is it. I take my time. Thank you. Over to Ramli.
Thank you, sir. On behalf of organizing committee, I thank you for your wonderful inauguration report. And with your motivation, we will proceed further. And the first issue will be my Dr. Namki show. Before that, I may request the participants to give us greetings. 1 minute to all the participants.
Ramli, special thanks to Director for giving me this opportunity to interact with students and staff of Hyper Article. Proteomics is an fascinating field, so I'm sure by combining of this and on the development of identifying the target voting place in Singapore. So I'm sure the students will learn at least few tips, those thoughts and incorporate onto dimension, each dimension in their ongoing research area. So I once again welcome all the students and thank the organizers for
Thank you very much. Definitely, the student will interact with you by follow up illustrations. And I will request that the phenomenon will give your readings. Morning all, good morning and faculty, speakers, and fellow students. Thanks for the organizers for organizing this particular session. Like I'm sure like, it's going to be one of the really fruitful and session that you can improve your knowledge and intellectual aspects. Mass spectrometry has been one of the forefront, right? Like everything would be the foreign domains, the foreign metabolomics or lipidomics, virus performa. Mass spec has become the forefront. And like as the data is creating one another, you know, the academia is routinely employed with industries rather than existing for the so-called what you said, big movement, right? Biosimilars, innovative molecules, so on. I'm sure like this particular section that you know made use both for your academic and for your further career. Without further ado, thanks for the opportunity. Into Dr. Saroman, and sorry already for the delay of 7 minutes. And with the time to support our scientific sessions, and our most respected speaker, Dr. Nandakesh over here, I may request Dr. Murali Kumaraswamy to introduce the first speaker of this series.
yes, thank you very much. And you're very good morning. Also, I'm very happy and prosperous to be at your house. I'm very glad to engage our speaker from Stanford, Kishore sir, who is currently the Institute President of the Department of Industry, India is something topic. He was the department December 2008, December 2011, in MSc Chemistry from the Banana University. After completing his PhD from the Indian Institute of Technology, Delhi, and received a postdoc contract at Dal University Institute of Science and Technology in the Texas of America. He jumped started from IIT Bombay in 1994. He has been a principal scientist in several kinds of issues of science and technology in Texas of America. His research interest into understanding the chemistry underlying the biological order system. His research work has contributed to the thermodynamic calculation Dr. Interactions, protein pharma interaction, and prevention of oxidation, fibrillation, by using a combination of earlier and manufactured. So far, it is also very ethical mathematics published by LC-HRMS. He has delivered in India. He was the president of Indian Chemical Society Mumbai, branch from 2010 and 2012. He has received award and gathered from Memorial Award for 2007 for contribution to the research and testing of India. Sir, with this welcome you, sir. Today, the Department of Physical Fine the nation. This is am I audible? Thank you for great words of introduction. And first of all, I thank Professor Ravi Chandra and head of the department, Professor Raman for guiding the administration and interact with the specifically stress on on the research that we carried out for quite some time. In this direction of national practice. And it has been quite interesting that people has been organizing several lectures by experts from different domains. In understanding the guidelines which are important for research, I have prepared my today's talk specifically targeted at students. So therefore, please feel free to stop me and ask questions at any time. Today also we have speakers who will uh, talk on different angles, but I will mostly highlight the physicochemical part in that further. One question is whether which generally comes to mind is that is physical chemistry useful? How it can be linked? What aspects of physical chemistry are important? How radiography can be used? Climate, such a for aspects. And we can show that how these so-called various thermodynamics measures when combined with spectroscopic methods, the radiographic methods, including LC-HRMS, are required if we want to, if we really want to have a target of conduct. So going back several years, during my field, where mostly the thermodynamics of some variable components was about capacities and other physical properties. I remember at that time that with the passage of time, after we start addressing the physical chemical aspects of biological importance, then one day we will also be involved as consultancy to pharmaceutical companies. So I would like to lecture in general, mostly this conference will now be recorded, mostly focused on our efforts in addressing this issue. Also, I think how we can do and MC that MS in our research. Also, when we talk will be there in the second half. Most of the technical aspects is better maybe I am sure that we covered over there. There are several applications of LC-HRMS and first of all regulations to dipole particle for having got this wonderful facility. It is essential in meeting the objectives of any pharmaceutical medicine. There are several components from six characterization, biology, activity, and then towards the target. Along this process, when we take molecular activities from synthesis, structural characterization to purification, this technique is a must. So I will share with you, discuss with you that how chromatography is important to this. Giving me my first introduction, whatever it is, my first question asked me was, what is the principle of separation? And I'm glad that I was able to do we're working on industrial water systems. And those who are working on synthesizing two molecular molecules for young and human cannot do this. So let us begin with the basics. But what is the chemical approach in rational design, and the chemical approach will benefit from if there are some several methods are required, several substances are required to target. For example, we not only video molecular activities, directors just mentioned that we need to understand that how these new molecular activities interact with the proteins, interact with the other targets. Thus, therefore, in addition to the structural characterization, as we have chromatography coupled with LC-HRMS, we talk about separation also. We must also understand that how the products that we are interested in synthesizing interact with the systems. So let's begin by the background. As it was over in the introduction, that we have used caloric methods. So we are going to understand the power. And today there are several caloric methods which will allow you to determine the result. Each of the direction down to let us say microcalories, microcalories. But sometimes when we think of the each of the direction, one column A, let us say, direction, one column, we assume that A B has been on, and whatever the intensity of interaction is, that we can the questions which are important to the answer from the research point of view are that when A is interacting with B, let us say a ligand is interacting with the protein, or a drug is is the process. it requires chromatography. You require something. You require structural depth. Otherwise, what if we look at this figure at the right bottom panel, where green bars are enthalpies of interaction, blue bars are just free energy and enthalpy and entropy, free energy, these are important parameters. And we talk about statics. We see that from the first class of the drug, 0 12 milligram, to the best in class of the drug, the green bars you see, and outwards is exothermic. There is an exothermic potential. It's not that the scientists, designed that way that over a period of time, you need to have drugs who will interact with the target in a coexothermic. And it just so happens. So isn't it that it gives direction over a period of years from the first in class to the best in class, more exothermic interaction that you have to keep of functionality. That's not functional. That is something. Now, we have this nowadays calorimeters available, as I said, which will give you the heats of interaction from micrograms, which are required because the interacting systems in vivo do not generate large amount. Now, as I said that, after the reaction is complete, how we carry on the reaction, how we go to listen to my previous lecture on this platform and remember that I discussed at that time. You put your protein in the sample cell, then you can put your drug in the syringe and you interact. And once the complex is formed, now can this now be coupled with chromatographic method of LC-HRMS to characterize the product, to characterize the complex, for structural verification, so that you can address these thermodynamic signatures accurately. See, one way, for example, if I am interested in understanding enzyme pattern, what usually we will do is we will take enzyme in this week and whatever is the substrate, we'll take in the cell. Now, as soon as the enzyme is injected into the cell, it interacts with the substrate, the product is formed. And as soon as the product is formed, you take out the product out of it and then perform with further analysis. Whether you want to do physical HPLC or you want to do LC-HRMS, depending upon some kind of. And the advantage of LC-HRMS, you are going to get the golden. So, some guidelines are always there. For example, in book schedule 5, we understand that molecular weight should be less than 500. There should be no more than 5 hydrogen bond donors. There should be no more than 10 hydrogen bond acceptors. Toxicity issues have to be addressed, and this log P, which we all understand, talks about also the hydrophobicity scale. I don't have to not discuss too much. The Liper family over here, they are well aware of this looking studio 5. But I always cover this with my lectures that for good oral bioavailability of a drug, the solubility issues and the membrane permeability issues have to be addressed. According to one of the reports, 41% of the marketed drugs, the new molecular entities which qualify into high permeability and high solubility component is only 5%. And 90% of the molecules fall into low solubility and low permeability. And that is a big problem in pharmaceuticals. So, even when we talk with our scientific colleagues, they usually talk about, their efforts in improving this function of the mind. First one. And otherwise, we need drug delivery mechanisms, suitable drug delivery. For example, we are interested in improving the exothermic interaction. Then rather, do we need introduction of more polar group or do we need introduction of more hydrophilic groups? We can check over here by taking this example of HIV protease inhibitor. If you add methyl group over here, you see the dissociation constant increases by a factor of 9. That means association constant increases by a factor of 9. But you are not giving this gaining much negative value with green bar. That means exothermic interactions are not achieved. However, if you introduce hydroxyl groups, then you get significant increase in exothermic. So functionality becomes very, very clear. So I will give a little bit more general introduction before I go further into application aspects. What are the important contributions for engineering bioengineering? New molecular entities or improvements in the existing drugs. What are the different factors which need to be taken into account? One is resolvation. Hydrogen bonds, that is once it is sitting inside the cavity, it will give hydrogen bonds or van der Waals interaction. Desolvation requires energy. Hydrogen bonds receive energy, van der Waals interaction, contribution will be whether it tap or not. And that's the second feature is very important. And therefore, is very important how many times keep in mind the target and that we require for this. How to improve the functionality so that we better finding and is we require and so that was what if you so I will not really go into this basic details, but what I want to show is that the various factors that we really worry about, that in which direction the reaction goes. What is the extent of reaction? What are the effects of temperature, pressure, pH, ion strength, or any metal ions everywhere on the position of the reaction? What is the enthalpy change of a reaction? What is the change in binding of ligand X for reaction? What is the role of functions? All these things we have to worry about. Now let me begin with a very simple case of design, very important industry. Historically, spectroscopy, various spectroscopic methods have used in studying the enzyme. I'll take a couple of examples. And then the passage of time, when there was more chromatographic methods, PLC. This offered real advantage to both the separation of reactants and product and also the amount of persistence. So see the keywords over here, the separation of the reactants and product. That is where your chromatographic part comes. The amounts of the substances. The amounts also chromatography will help. But we also need to have a structural distribution of whatever is left or whatever is formed. And that is where chromatograph coupled with mass spectrometers, this leads to an additional biological capability. Therefore, it becomes a very important tool in the research which is directed towards drug design and development. Of course, when one is dealing with HPLC for DC, detectors are important. And when I'm sure I've already learned the principle of HPLC or might have yourself HPLC research. There are various detectors one can do. One is the usual invisible spectrophotometer or fluorescence if the molecule or the product form is having fluorescence properties. And if these properties are not there, reflective index is another method. Electrical and thermal conductivity, radioactivity, etc. One can use NMR to the date. But let's see coupled with high resolution mass spectrometry, where we talk in terms of mass and charge. This becomes an essential method today. Let's take some examples. If we talk about enzyme catalyzed reaction, for example, RGD to ROD, this reaction can be carried out by RGDs. And this reaction is important in the final step in the metabolic reaction. There are various metabolic cycles in which the various steps which are catalyzed by enzymes, but today are not totally understood in terms of thermodynamic. And now if we are interested in, let us say, the conversion is part into molecule by the presence of urea. And I not only want to characterize my reactants and product, but I also want to have other parameters which will help me in understanding other reactions. That is the beauty of thermodynamics. In a metabolic cycle, if we can give thermodynamics knowledges or understand, then the other reactions to the metabolic pathways, we don't have to experiments. We can actually calculate by those processes now. It appears simple, but in order to do an experiment, for example, as I just mentioned, this RGD catalyzes this RGD, this reaction involves. But we must understand quantitatively how much are the things. Is there any side product? Yesterday you were very much important, you were very much interested in understanding that are there any other impurities along with the synthesis. And I have evaluated many 6 from pharmaceutical industries, including Dr. Reddy's lab, where the whole thesis is focused on this identification of impurities and method development, including this LC-HRMS. For example, another reaction arginine to citrulline, which is actually catalyzed by amylase. This reaction, the citrulline, we understand the medicinal importance of citrulline, which is actually used in the treatment of Alzheimer's disease, dementia, and muscle weakness, etc. So why I am discussing about this? There's a couple of more examples I'm putting over here that we have actually studied. Is this aminotransferase catalyzed reactions where this amine group is actually transferred and ketone group is transferred. Or this is, for example, conversion of alanine or this conversion of alanine to also alanine and also proteinic acid, pyruvic acid. It is really very, very important processes. Right? The analysis part. Just little bit insight, physicochemicals. If we are interested in analyzing this reaction, for example, ATP plus water, that is the hydrolysis of ATP, which forms ATP and orthophosphate. Those who are interested in understanding mechanistic details or would like to understand the physical chemistry underlying the process, want to give the correct value of free energy change, will try to recognize that what are the various species present in this. In this, for example, in this reaction, the various species that you can think of is ATP4 minus, H-ATP3 minus, H2-ATP2 minus, then sometimes they are by doing the reaction to attract histamides or other metal ions. And the apparent equilibrium constant. Apparent equilibrium constant we write for this. Concentration of ATP into concentration of orthophosphate divided by concentration of ATP divided by C naught. I've addressed here to students. You should be clear that the equilibrium constants are the original quantities. Many times we see the equilibrium constants we write units, but the physical chemist will not write units in equilibrium constant. And in order to take care of the units, you see here the denominator C naught. C naught is 1 over per decimal unit. But this is just for the information of those students who are not clear about that the constants that I mentioned earlier, irrespective of this activity. But just bear with me for a couple of minutes more in addressing the physical chemistry. The total concentration of ATP will be the concentration in all possible forms. And the other parameters which we require for the optimization of the process are temperature, pressure, pH, ionic strength, and px. What is x? X is, for example, magnesium ion or if you want to add it. And then you are worried about delta G naught minus R. This is an important parameter because it talks about the amount of product form equilibrium constant. And the corresponding, you can talk in terms of the standard reaction gives rate. And those who really want to go into further details will understand that the equilibrium constant is not actually in terms of the concentration. It is actually in terms of the activities. So therefore, this is, if you want to now really go into research aspect of that, the point of the intermolecular, other effects of intermolecular interactions, you will talk about activity and you need to have knowledge of activity coefficients and therefore the divine function. I will not go beyond this, like that's the physical chemistry of the equilibrium. But one is said that the equilibrium constant is important. And we should be able to understand, we should know how to write it. Most of the time we just write it in constant as the ratio of concentration of products and reactants. But actually it is not concentration, it is activity. And if we have minor solution, then it might happen to be. So what it has to do with the chromatography or the topic for which we have assembled. When I take lectures on thermodynamics, in my class, I usually ask the question. Then if I give you some reactants, reactants will perform some product. This is a drug for any biochemical reaction as Let's just start with, let us say, enzyme catalyzed reaction. What to form? Convert one amino acid to another amino. How will you determine the value of equilibrium constant? Equilibrium constant is important because you want to have a high value of equilibrium constant, you want to promote. How will you practically in the laboratory determine the value? So usually, students will take some time and definitely some French students will come up with the answer very quickly. Is that since we are for equilibrium constant, which is the ratio of the concentration, let us for the time being not talk about activities. The ratio of concentration that is in the laboratory, I should be able to determine the concentration of the reactants and products. To understand what are the products formed, first you need to separate the various components. That is where your LC part comes. And then your characterization. That is where your detection comes. Now we have various kinds of detection. If these are amino acids can be separated by liquid chromatography. Or if we have a combination, LC-HRMS, wonderful, not only the separation, you also have the structural characterization. So once you have this information, you can get the practical way of determining equilibrium constant in lab. So now the question is, the next slide. Let's take this simple chromatogram. And I go back to my older example of enzyme catalyzing. This is a typical chromatograph. And how do we determine the concentrations? Of course, those who are, I'm sure that most of you already know that how to quantitatively get concentration from this. We need to first calibrate and then from the response factor, which is, the area connected to the area and the curve of whatever This is the, for example, this is for the tryptophan. If we are interested in finding out the concentration of tryptophan, we will see this. We can know the concentrations. If we don't know what is the product that is made in your mass spectroscope particle, that is made in your MS particle, but if I want quantitatively the value of equilibrium constant, no. How do I present? I'm only talking about the values of equilibrium constant, the values of enthalpy, entropy, etc. But I will later on tell you that where these are important impression. How these are important. But before that, we need to have follow characterization of our sample. Otherwise, we will be addressing raw reaction, raw signatures, thermodynamic signature. So, in a given reaction, for example, if the reaction involves tryptophan, if I can determine the concentration of tryptophan accurately, the minus cytotoxic reaction we can also determine the concentration of other reactants. Right? And using your LC-HRMS, you can have the structural identification of the compound variant. We can have like now, let us say, in addition to this equilibrium constant, now I am interested in understanding the enthalpies, which can be determined accurately by using calculus. So, as I discussed earlier, that if you are interested in understanding the primary conversion of one reactor to another product, this product is formed, apply those corrections to the enthalpies of the reactor, because the process might not have been 100% complete. The extent of the reaction might be 0.99, 0.90, 0.80. So therefore, those corrections apply if you want to stress the problem. So those who are interested in understanding more about this can refer to our one chapter in the book Chemical Thermodynamics, Chemistry for 21st Century monograph, which is published by the International Curated Libraries. Chemistry method development is very good. And today, when we talk about the efforts of various pharmaceutical industries, one key process in the drug design is the method development for the identification of the product, not only the identification of the product, but also the but as I just mentioned some time ago that I have reviewed many theses which are coming out from the large amount of time is and efforts are spent on the metabolism, in which LC-HRMS is a major. And the various parameters for method validation. All of you know what is the validation of any analytical method? It's an act of providing that any procedure, process, equipment, material, routine, or system performs as expected under a given set of conditions and adheres to all these parameters. Accuracy, precision, the students must understand the difference between placing season very just like here Lambert's law is not always applicable. The developed method may not be applicable under all concentrations and rates. Here and rate are important parameters. Limit of reduction and quantity. I'm sure that the students understand the difference between reduction and quantity. You must read about it. It has to do with the voice rate of ratio. And some factors only have to apply with the noise, the reference, or in the blank, convert the limit of reduction and limit of volume. Now, at this point, I would like to connect with equilibrium process, limit of reduction and limit of the quantity. Please, can I connect with this? Suppose in the peak in my tomato plant is very, very small. Very small, that it is almost coming in the range of limit of quantification or limit of reduction. So if I cannot, or let us say it's the product or the reactor, so PP will be LC output, chromatographic output. And we are sure that the separation of other components are not going to take place. Then what value of equilibrium constant do we give? We cannot give a definite value to the equilibrium constant because in the denominator we cannot see if we don't see any P. In that case, if your LC-HRMS ensures that there are products and reactants all present in the mixture after well separation, then one can use this limit of reduction or limit of quantification, whatever the smallest number you have, put that in the denominator and say that your value of equilibrium constant is higher than. We cannot give a definite number. We can always give a lower that the equilibrium constant is higher than. Then one has to worry about its selectivity and specificity, robustness, properties. And at the same time, we need also understand that the method development is a continuous process. The method developed for a certain set of molecules may not work for the other set of molecules. And therefore, this is a never-ending problem. And chromatography and more importantly, LC-HRMS are important component of this process. And everything has to follow the ICH guidance. Some of our efforts. In other than the enzyme processes. So one is towards the synthesis. Whether it is done in a traditional manner or it is done by an enzyme catalyzed reaction. We all understand that whatever way we proceed, we need to care about the amount of product, efficiency of the process. address this issue of what is the effect of glycation on drug transportability of hypersyllabic? Implication is that. So as was I once again highlight as directors are told in the beginning that we interact with the targets, or other targets, understanding those interactions. I will cite here an example of one pharmaceutical company which approached us sometime ago. They had some, I will not name the company or name the product. They had synthesized some molecules and those drugs. The FDA for those drugs, FDA wanted data on how this molecule acts in the cinematic. And for that, they approached us to provide insights into the binding mechanism and binding strength of those polypharmaceutical synthesized molecules or whatever drugs they had. The syrup, which that David also motivated the term. So this understanding these interactions is very, very important. And I'm sure that my next invited speaker is going to talk, until beyond further and they highlight the methods in building LC-HRMS into this. He also our group has been studying the interaction of variety of drug molecules with genes. And since serum albumin is a transport protein, therefore understanding the interactions here becomes very important. Because the thermodynamic signatures, delta G, delta S, delta H, are not just numbers, but they tell us about the type of interaction, the nature of interaction, and the role of function. So the question that we wanted to address was that when the glycation takes place, does it affect the drug transport? And of course, we carried out a non-enzymatic glycation just by the presence of glucose. And I'll show you some of the results. We started analyzing the advanced glycation end products after a specified time period. And I will not go too much into our experimental aspects. Display over here that we did add so much glucose we added and we are physiological information. Okay. And then we collected the samples, over a period of time and characterized different peaks. So means whatever this advanced glycation and products, anhydronic products, shift bases. So what are these glycation and products? We carried out various kind of assays. The activity reaction, EMS PPA assay again for the sake of time I will not go in details, but I just want to highlight that these are the assays which are important in this aspect. And we employed a variety of methods in the characterization of its AGEs. And then, in that, LC-HRMS was one of the methods that we used in the characterization of this. It is, in addition to all the other methods, for example, a variety of techniques like from leading from simple UV visible fluorescence, CD, time result fluorescence, marking tops, etc., etc. All this we try to use to give the final outcome which I will share with you now. And we could characterize whether we want to what are the various products and now you see there are various information of eight areas which are applicable. Now once you have this kind of this, is it affecting the drug transportability or not? That was the main question that we want to So in this our chromatographic methods are very helpful. So again, as I said that employed a variety of methods in that. Let's not go too much into that. And we could actually calculate the number of molecules attached to HSA from which it was possible to understand percent linkage. And then we studied the transportability of the library over a period of time. So obviously, this question is that the implantation has taken place. Then whether different transportability is in the right direction or not, so much it has affected, then we quantitatively address this. So one way is after the characterization and the characterization we used various techniques including the LC-HRMS. Then we further study the interactions. And interaction is fine with isothermal temperature. And then, as I mentioned that isothermal temperature there are three parameters from one experiment. The binding constant, energy of interaction, all these are important. Because this gives binding strength, how the molecule is formed. The enthalpy of interaction, for example, here is -1. -1 is not there. That means the predominant contribution of polarity is polar energy. There is variance or there is a large variance. And secondly, the important part we have. Positive entropy is plus or the spontaneity of the process. The association will be more possible. Again, I'm addressing this. If I say that there is an association and I say there is an entropy increase, it is not going to be because the molecules are combining A is interacting with B and one then actually the difference is decreasing should be negative, whereas should be negative. But actually sometimes it is not and that is where you try to understand that these substances. That means if the atomic change is largely positive, there are large molecules of solvent which are released as a result. words, there is one molecule which is solvated, there is another molecule which is solvated, when they are interacting, the solvated molecules can increase the water and thereby generate blood. So even though what we observe that the pumps are not very big, the interaction is technically overall technically as well as delta C. However, if you look at this IBC profile, the values of K that would go compared to this is unlike an example in GS. There's a likelihood from V1 to V4, for example, you see here. At least up to V3, there is hardly any change in the value. So this is an important result that we the various drugs will this is the data to follow also. We have taken other drugs in the what we observe that the binding constant values of binding constant either understand. So this is a management that is working but we see that not significant it is not an issue. Rather, in some cases, it shows this kind of. So let me also introduce again another method, which is helpful in these aspects. Is the thermal scale. In addition to all other characterization techniques, in rational representation, it is important to understand that the target that matter consideration is a protein. As a result of point, as a result of interaction, the conformation of protein is intact. How do we check that? There are various methods. There are spectroscopic methods. One very good signature, very widely used in pharmaceutical industries, is differential scaling calorie. Because when you treat the to be signature being provided, what you do in DSP, differential scaling calorie, is you plot heat capacity against temperature and it gives some particular signature for a protein. And then, whether it is a glycation or it is a binding, the changes in this signature tell us stability. So this is one method that we really use in our research in combination with the other methods that we have done. The purpose was structuring property related to structure. That is where you characterization techniques will come in. Property. Properties will emerge from the relatives. And energetics. Energetics will also emerge. So if we can correlate this, what I have shown this can also be coupled with very effective structure company energetics correlations, and such type of correlations are provided derived by elements or results of or modify the existing drugs because this is what you are interested in, how to function. There are I will briefly talk about that. So, anyway, what we observe here that in function we try to connect the function molecule versus the molecule which have the rates. That which one has better again, this is, I have talked this slide specifically with solutions. This slide especially one of my I only graduated based upon it demonstrated in translating the research ideas that we have is in some action which can be easily understandable by them. So she submitted this scientific story by it was selected for this subject. So the if we represent in these cartoons, cartoon characters, the laymen are able to understand that what the diabetes, but what to, the drugs may not understand where to go or not. No, no, it is simply not. It will be trivial for the layman to understand this kind of translation. Now let's spend time for. And as I mentioned, that this kind of relations are extremely important interaction. So, how much time I have for, and I will plan my remaining talk accordingly. Yes, up to 1 o'clock actually. I mean, we can before 10, 15 minutes so that the audience can interact with you. So also. So the next question scheduled. Yes, sir. Yes, sir. Next will be scheduled by 12 o'clock. Well, then I should say. Okay, so just one more aspect which I will quickly go through is that hopefully the next talk is going to talk more on proteomics. But protein folding problem is something which is still unresolved. And if the protein does not solve a normal folding and deviates at early stages, you can lead to the separate fibrates, which are unwanted and lead to neurodegenerative diseases like Alzheimer's disease and Parkinson's. And but today we are struggling to find suitable medicines which can prevent this process, it will stop this. We understand that once that gets here, that prevent associated. But of course not that is it. They also try by the other things like all the other drugs like cortisol and of course imagine this mentioned this basic representation so that the layman can understand that this
including LC-HRMS, yeah, into the national level side. But I just picked up a few articles with comparison to one. One is, for example, here plasma procurement changes in patients. We don't popular arterial fibrillation, and this is a pilot study. I found this paper to be very good, where it is kind of pain. And this is one environmental area. One pain is quite common because it can see the developments. But I thought doing a snippet highlight about what because if you just see the red and came across. These are all 2021 articles, and it's a month review, it's maybe it talks about multi-dimensional LC-HRMS, the next generation characterization of antibody-based therapeutics. So, these may be very useful particulars. Let's further learn about specifically about LC-HRMS. So with this, I would like to end my presentation and would like to invite questions.
Thank you very much for your I personally I am passionate about like transport and transportability by applications and all. I request all the participants to put their queries and we interact with the response person. And I will plan.
Professor Kishore, it was a wonderful, the talk. We all enjoyed. I feel that the master being generated, model, the data, what you would share. I have a question. Please, basically, one aspect is the history, and another aspect mainly metformin. Metformin, we are increase its efficacy. The metformin declared widely, but at the same time, the metformin, availability for biological food is just 50% or less. In this logic, how the metformin, the biomarker absorption be raised or improve its body content. This is the diabetes, what the point you present.
Right. What we actually observed was that the extent of glycation that did not affect the this binding ability of spectrum. So that was our major observation. We did not address the other aspects, specifically I think the point which you are highlighting did not address that. But specifically with regards to insulin, it is, even if we talk about this, the association of hybridization aspects of being connected with these are diseases. That also we have not yet studied that what is the data that we showed was on the prevention of hypertension by ionic liquids, because ionic liquids, the ionic liquids have shown to provide a good amount of stability to the lungs, biocompatible. And therefore we were interested in understanding that what what is ideally to whether they are molecules prevent migration or activation or so that we have studied here process of writing. And this metformin is another drug that we are planning to understand. But as far as the data that is shown, that was only with metformin, and most of our main focus was on understanding whether all these glycation anti products they affect the drug transformation.
Yeah, I understand. Thank you, Professor. There is a concept there, that's the reason. So we can discuss further later. Right, right.
Well, good afternoon, and I just have a little queries I think about the suggestion and a input on this I got. Right now, this bacterial resistance is one of the going to be a next pandemic.
Yes.
Because most of our antibiotics are basically polarity. Any visual exam or aminoglycoside, so all are like multiple polar functional groups, and they have a lot of problem with the drug permeability through the cell wall or cell membrane of the organisms. And is there any support like how we can increase the transport across the membrane forwards or polar, like basically polar drug, and more commonly, and we
It's on the drug delivery also. Right? For example, there has been a lot of research on the drug delivery system which are of nanosecond and which can actually carry the drug along with it. So this we are actually going to move in this direction by the previous river system, and where the drug can actually be even not with non-covalent interaction or covalent or non-covalent interaction combined with this suitable drug delivery system so that there is a target specificity and the membrane permeability can operation. So we are addressing from a different angle. Of course, we can discuss on the
sure, thank you. And audience, please, participants, scholars,
especially students like yes.
You have mentioned that equilibrium constant, right? Then you have mentioned that there are chances that there is no peak, and there are chances that the reaction is occurring and there is peak, and then we should take denominator value very less value, right? So, how you can predict that reaction has occurred without seeing a peak, sir? What?
That is where this the facility which has been installed now is going to be very, very good. If you don't see, first of all, the separation is very, very good. If you don't see in chromatogram, you don't see a peak, then either it is embedded under a major peak, right? That means separation has not taken place, or it is well separated but it is not showing. It is not absorbing whatever detected you are using. So this HRMS is going to be can be tracked to identify whether the product or whatever molecule. If you don't have that, then there are other factors to identify whether the expected molecule is there or not. I think I answered the question.
Yes, sir. Yes, sir. Sir, there is no compulsory that we have to take a low value, right? like in denominator.
Is only after you are sure that at this point, for example, if it is 50%, and you have a peak of cryptogram at certain time, so you are assured that cryptogram will come over here. And if you are able to separate the molecule, you are assured that you are able to separate, and at that time, that is not appearing, that means the amount of cryptogram present is very less.
Thanks, sir. Thanks for the informative session, sir. It was a really wonderful session.
Thank you. Covered a lot of basic chemistry also into this. If there are any clarifications you want to have on those, please feel free to ask. There are no questions, then in the last day of the year, and then let us hope that we have a very, very happy new year, 2022, and we get rid of this software. Thank you. Thank you very much.
Request Dr. Murali, can you please propose a tag with the questions?
Yeah, sure, sir. Sir, thank you very much, sir. Thank you very much for this wonderful session. Yeah, of course, it's really useful for our students in particular because we covered like a lot of basics, terminus and lipid scheme and all. So on DeFi Markov theory, very importantly, we gave some information about abstract program, which is actually most of the students get educated through these programs. So thank you very much, sir, for your time, and wish you a very happy new year. As I said, like this next year, 2020. Thank you for the run. Thank you. Thank you.
Thank you, sir. Thank you very much, sir. Thank you very much for your valuable time.
Yeah, please go ahead. Thank you, Professor Kishore. Happy and prosperous New Year. Over to Ramalingam. You can go ahead. Yes. So sometime, Professor Kishore, I wish that your presence over here, the campus, I'm expecting this event itself. So that's the reason I asked to write also.
Right. I will
See here.
right.
Yeah. Thank you.
Dear participants, the next session will be by Dr. K. Balamurugan, Professor Department of Biotechnology, Vellapur University, and Dr. Balamurugan, sir. Sir, we proceed.
Yeah,
You're ready, sir. Okay.
So, very good afternoon, sir. So, I'm very glad to invite this speaker. Balamurugan sir has 28 years of experience in different area of research, in particularly post-rapid interactions, animal model system, using a candidate events, functionomics such as genetics, proteomics, metabolomics. Currently, he is a professor in the Department of Medical by University of Tamil Nadu. And he also worked on multiple projects of the different participants, PSC, IC, part of PG. So far, he has awarded 14 PhDs under his excellent leadership. Professor Balagan, PhD from, he completed PhD from Banaras University.
biologically life-science related proteins, peptides, antibodies. Most of these molecules, right, be it small or large molecules, they are very labile. They are not really resistant to very hard kind of ionization principles. What do I mean by hard? For example, FTAP, fast atom bombardment. For example, EI, electron ionization. So these kind of hard ionization techniques, they would tend to degrade when you are trying to ionize them using these kind of techniques. Your sample analyte might degrade. You may not get informative spectrum. So that is where these two gentlemen they played a very key role. They developed something called ESI, electron-free ionization, and MARTI. Now, having said that, these two techniques are now being routinely employed, be it small molecules or large molecules, whatever it could be pharma, it could be biopharma, it could be any other industry, or it could be academic applications like proteomics, metabolomics, so on and so forth. You would very frequently encounter either MARTI-based instruments or 3 major classifications, right? One is called Ball trap, which was named against Professor Wolfgang Ball, the one who you can see it on the right hand side, bottom hand. The other one is called Penning trap. Again, that has been named after Professor Scientist Paul Penning, who is the postdoc guide of Professor Chapman. So these two gentlemen, they have been jointly awarded the Nobel Prize in the year 1989 for developing ion trapping techniques. The other trap is called Kington trap, Ball's trap, Penning trap, and Kington trap. So now Ball's trap is nothing but the quadruple trap and the other trap that you routinely see in the, let's say for quantitative labs. Penning trap is nothing but the ST, Fourier transform ion cyclotron resonance mass spec. And Kington trap, Kington is the name of the scientist again. So he developed and published a theory in the year 1923. So that particular theory was worked, reversed by almost 2 or 3 generations of scientists. Finally, in the year 2000 and 2005, this gentleman that you are seeing in the bottom panel center is Dr. Professor Alexander Makarov. He is currently heading our R&D efforts in Thermo Fisher. So he was the one who had derived, redeveloped, re-improvised the Kington theory and named it to be orbit trap. Kington trap is nothing but orbit trap. If you could see this small device like atom component in this hand, that device is nothing but the orbit trap. Right? So let's move on to the next slide. Currently we are in slide 4. So this particular slide, it shows with the basics what is a mass spec or what is mass spectrometry all about. So mass spectrometry is all about, it's an analytical technique. It's based on the motion of charged particles. That's why we are ionizing it. If you don't ionize it, you will not be able to distinguish the movement of the ion inside the mass spectrometer. So mass spectrometer, be it a small instrument, benchtop, or a relatively larger instrument, one has to discipline. One has to dictate the movement of the ion. So that sort of a discipline factor you will be able to achieve only if you ionize it. Once analyzed or ionized, they carry a charge. Once that they carry a charge, they tend to respond, right? They tend to respond to either the electric field or the magnetic field. So that's the basic logic of ionizing. So whatever that we are detecting is all ionized molecules, it is not neutral, right? So it is based on the motion of such charged or ionized particles in an electric or magnetic field, aiding with the measurement of the implied field. So since that they carry a charge, it is always mass by charge. So the bottom line is, once if you can elucidate, calculate the charge factor, you will be able to measure or quantitate or elucidate the molecular weight of the given analyte. So that's the fundamental logic of mass spec. Now this particular logic is what has been extrapolated, improvised, and then it is being now routinely used for both in academia and industry. So having said that, there are two major extrapolations, or I would say rationals. One is the so-called gas-based behavior of the molecule, which is nothing but the intact mass, MS1 analysis, where you will only measure the molecular mass. And from the measured molecular mass, you can elucidate the formula or predict to some extent the structure. So that is point number one. Point number two, gas-based dissociation behavior. That is nothing but the MSMS. So we call it MSMS or MS2, MSN. These are different names. Ultimately, it all corresponds to gas-based dissociation behavior. So based on these two behaviors of a given analyte, we end up designing different kinds of experiments. It could be identifying their mass, identifying their names. It could be in the context of proteomics, metabolomics, lipidomics, biopharma, pharma. Fundamentally, all these things come under either one of these criteria, either MS1 or MS2. Furthermore, we also we try to target. You either target it at the MS1 level or at the MSMS level. Thereby, you will be able to selectively quantify them. So the earlier one, what I had shared was qualitative analysis. The second one that I am trying to share is nothing but the quantitation, quantitative analysis. So these are the two major or two broad experimental designs one can achieve using a mass spectrometer. Right. So now let's go on to the next slide. So currently we are in slide 5, wherein I am trying to show you the box plot, the thematic box plot of the typical mass spectrometer from left to right. So here you have the sample introduction interface. So you infuse sample either through a syringe pump or it could be through an LC, lipid chromatography, EC, gas chromatography, or even CE, capillary electrophoresis. Once sample has been introduced, the first thing is obviously it tends to ionize. So we had talked about ionization. So you can see in the bottom panel the different representative different ionization components that are available currently. Once they ionize, they get analyzed again. Based on analyzers, you have these many different techniques of analyzers. Ultimately, you end up detecting the molecule or the analyte, and then it gets further processed using bioinformatics or computational programs, and that would give you the output. The output could be simply an identification or a quantitation. That's the bottom line. Now let's go to the next slide. Currently we are in slide 6. This particular slide will explain you the working principle behind the so-called orbit trap mass analyzer. So if you could see here, there is a cylinder-like structure, right? Cylinder-like geometry. So this geometry is nothing but the orbit trap analyzer. So the gray region that you see here, the outer gray region, it corresponds to the one pair of outer electrodes. And then you see a central orange color region, spindle region, that's the central electrode. The three color rings that you are seeing are nothing but the ion populations. So now these three different ion populations, they are moving around the central electrode on a fixed path. This fixed path of movement is nothing but the orbit. Basically it's orbiting, right? That's why from a scientific technical standpoint, they call it orbital trapping of ions, orbit trap. Now if you could visualize this carefully, they move around the electrode on a fixed path with certain level of frequency. So this frequency of movement, it generates something called the image current. So if you could see in the center of the slide, this particular graph. So this graph is nothing but the transient graph, or I would simply say image current detection. So the x-axis is time domain and y-axis is amplitude, measure of the frequency. So you can see that there are spiky graph kind of stuff. So this corresponds to the transient movement or the frequency of the transient movement. Right? So this time domain signal is later transformed using the FT algorithm, Fourier transform. So from time domain, you are getting it translated into a frequency domain. And this frequency domain has both frequency and intensity. Right? Ultimately, this is again being translated to generate the so-called M by C spectral pulse. This is the overall orbitrap analyzer working principle in action. Now, one important thing is that, as compared to the other mass spec platform, like in case if you have got a chance to read about the other instrument, how does it work, how does it detect molecules, in all of it or in most of the mass spectrometer platforms, ion populations, they physically interact as the detector plate. The detector plate would be EMT, electron multiplier tubes, PFT, photon multiplier tubes, diode based electrodes. So if that's the detector plate, the signal gets amplified and ultimately gets detected. Having said that, day in, day out, when you're exposing a detector to some sort of an ionic interference, it could be the ion of interest or the other ions that is there in the sample. So that is going to saturate the detector. That is going to compromise the lifetime of the detector. That might also lead to memory effect. So I'm sure like from a chemistry, biochemistry perspective, you must have heard something called carryover. Right? The carryover we see it in chromatography. Similarly, memory effect is something that we see on spectrometry. So random sustainments of analyte or analyte like signal or analyte derived electrical artifact or electronic artifact. That's what we call as memory effect in action. So all these consequences are expected if the ions are being made to physically interact with the detector plate. That is not a concern here. So by no means the ions they physically interact with the detector. It is simply the movement or the frequency of movement that is exhibited during this transient leg. That is what is being recorded and translated into M by C. Until unless the ion exhibits a very near, cohesive, confined, disciplined movement, the frequency graph will not be generated. Be very, very specific. That is the main reason why you are getting very high mass accuracy. The other thing is, as a user, you have the liberty, you have the freedom to make the ion to move it as long as it is required. So if you could see here, it is moving around the electrode. So as a user, you can tell, I want this ion to move for 10 milliseconds, 100 milliseconds, 200 milliseconds. That time factor is going to directly translate it to higher resolution. More resolution, which means you are dictating the instrument to acquire the data for more time, more transient length. They are having said that once you get very high resolution, ultimately it gets reflected in terms of mass accuracy. That is why you get very high resolution and very high accurate mass data, which is simply not possible always in other instruments. That's the bottom line. When we are currently in a slide wherein I am trying to show the instrument schematic. So from left to right, you have the ITC2, where the sample gets stabilized, then enters into the instrument. And then you have the FLEX, which is essentially for focusing, transmitting the ion. And then you have some sort of an H-shaped, active ion P-type that is for selectively moving, transferring the ions of interest. In other words, for deflecting, neglecting neutral interference. And then you have the segmented quadrupole that is for isolating the mass change or mass of your interest. And then you have the ICDs, independent charge injector. So the subsequent slides I will be talking about ICD. Like the way that I have framed this particular session is that when you, if at all you guys get a chance to look at the instrument and the instrument hardware interface, you will come across two types of parameters. One parameter is like you can understand it. Mass range, what is the M by C range, whether you want to do full MS, MSMS, or resolution. So there are certain parameters that you will understand for sure. Those are very common scientific technical parameters. But there are certain parameters that are exclusive to orbiter. So one such parameter is AGC, automated gating control, and the other one is fill time, injection time, IT. So this ITD, independent charge reactor, it plays a very critical role to determine, to measure AGC and IT. So in subsequent slides, I will show you some tips and tricks on how to set AGC and IT. Other parameters are understandable, like you can set it based on your sample design principle, right? So following ITD, we have the so-called IRM, ion routing multipole. In much simpler words, it is nothing but extended octopole cell with multiple confinement units inside it. The logic is that Like in the beginning of the slide, I told you, right, mass flow is all about two things: gas-phase behavior, MS1, gas-phase dissociation behavior, MSMS. Now, in different instruments, we try to attain the dissociation with different sort of principles. In certain instrument they call CID, collision induced dissociation. In our instrument we call it NTD, high energy collision and dissociation. In certain other instrument they use ETD, electron transfer dissociation. So these are different kinds of fragmentation techniques, dissociation principles. So from that particular context, if you ask me where does that event take place, so-called gas-phase dissociation or the so-called NTD-based MSMS. That particular event takes place in this particular component, ion routing multipole. Now, why do we have multiple confinement? If you could see here, there are different cells, right? Why do we have multiple cells? Now, from a scientific technical standpoint, we, one day or the other, we end up, encountering molecules from diverse sources of diverse physiochemical characteristics. Let's say it could be size, it could be charge, it could be the structure, cyclic molecule, linear molecule, branched molecule, so on and so forth. Now, all molecules, talking about the gas pressure that is being sustained in the instrument to maintain vacuum. So because vacuum, there is a little bit of a vacuum gas, nitrogen gas actually built in the instrument, right? So having said that, you need different levels of gas pressure to be regulated to sustain and to effectively measure different kinds of molecules. It could be large molecule, it could be small molecule, it could be cyclic, it could be linear. So in that particular context, one should have dedicated cells to collect and sustain, let's say, parent molecules, the bigger one. Similarly, one should have dedicated cells to attain collision-induced fragmentation. You need to fragment the precursor. Again, one has to have dedicated cells to sustain the fragment. Then the sustained fragment is then transferred. So all these different kinds of functions are being performed in one cell. Therefore, this one cell is being designed in such a way it will have multiple units, multiple confinement units, each of it with different levels of gas pressure, so that you will be able to efficiently attain the so-called parent to daughter ion conversion, precursor to daughter ion ratio conversion. That is nothing but MSMS, right? So that is the logic behind having a multiple confinement cell. So it's nothing but extended octopole with multiple confinement cells. It's called ion routing multipole. Following that, of course, you have the main component, so-called orbital, higher resolution orbital, right? All right. So now we'll go to the next slide, slide 11. So this particular slide essentially shows you the functions of different hardware components that we had seen in the earlier slide. So you can have a look at the bottom schematic. This is what is there in your lab, right? The front one source region is for ion control, for pumping. And then as I told you, this is for removing neutrals. Purple is for isolation. C-trap is for accumulation and injection into orbital. LCD is for fragmentation, and orbital is obviously for, these are all like analyzing and detecting. Let's go to the next slide. Alright. Now coming to experimental design. Setting up a method in much simpler terms, right? So what sort of mass range needs to be set? That is what is being shown in this particular slide. This is the mass range of the instrument. Your instrument can acquire as low as 40 and as high as 6000 MPC, right? However, there is a logic. Since it can fit 40 to 6000, it doesn't mean to feed 40 to 6000. No. So if the first mass is greater than or equal to 150, so first mass is this one. Then set the last mass less than or equal to 50x times of the first mass. Getting it? So for example, let's say you want to upgrade from 150. So in that case, what is the deductible or cannable range? That's what this particular logic means. So in that particular context, let's say your first mass is 150. So the last mass has to be 2250, 15 times 150. Right? Similarly, for some reason, let's say you want to acquire very low molecular weight, for example, 50 MPa. So if the first mass is 50, then the last mass, make sure it is only 10 times. For example, 50 to 500. That's the logic. Similarly, if the first mass is 40, the lowermost thing, then it is better that you set it to 40 into 5 times. That's it, 200. This is the logic. This is how you need to set the scan range, mass range. In the subsequent slide, I will try to apply this particular logic, and I will tell you how this particular thing gets applied for a proteomics or for a metabolomics experiment, right? The next thing, bottom table is about isolation rates. What is the isolation rate that is achievable, right? Quadruple does the function of isolating it. This particular thing, if you could see here, recommended setting, that is for qualitative experiment. Large scale proteome, large scale metabolome, screening, unknown screening, those kind of applications, those kind of experiments. This particular thing, the table that you are seeing at the bottom, it is going to do with targeted applications, quantitation. For example, if you are trying to set something less than 400 or equal to 400, isolation width can be approximately equal to 0.4 or a bit more than 0.4 AMU, atomic mass unit. Similarly, for 700, it could be 0.7. Likewise, for 2500, it can be even 2 or even 3 units. So greater than 2500, you cannot isolate the precursor. So these are something that you need to keep in mind when you are setting the parameter in the instrument method interface. Right? So now let's go to the next slide. So this particular slide, there is a direct correlation between resolution, transient length in terms of time, this millisecond, and scan speed in terms of hertz. If you could recall from my earlier slide wherein I showed an animation of 3 color rings that are moving around the electrode. So they are moving around for some sort of a time. I told you time. More the time, more the resolution, right? That particular logic, try to employ it here. If you see here, time is 32 milliseconds. Resolution is 15,000. And scan speed, number of scans per second, 22 hertz. The minute you are making the molecule, same molecule to move for a longer time, let's say 512 milliseconds, immediately the resolution gets translated into 240,000. However, the scan speed is only 1.5, which means approximately 1 to 2 scans per second. So this is the logic that you need to keep in mind when you are trying to design, set up the instrument parameters. What sort of resolution I should keep for this kind of a molecule. Let me try to explain this in an example. For example, antibody. Let's say you are trying to acquire 150 kilodaltons antibody. What is the resolution you want to keep? So in that case, you should keep 15,000 resolution. Why? Antibodies are, as I told you, it is 150 kilodaltons. Very large molecular weight proteins. So since the protein backbone is very large, the number of photolation sites, charge sites are also more. So one would end up getting 40 charges, 50 charges. So those kind of molecules, if you make them to move for a longer amount of time, they may tend to decay. Therefore, your idea is to acquire an antibody and make sure it gets separated from an isoform or a glycan isoform perspective. I know that I might sound a bit complex, don't worry. The subsequent slide, I have a slide wherein I will show you what an antibody spectra looks like and what do I mean by antibody glycan isoform, right? I'll show you all those things. In this slide, I'm just trying to give you some hints. What if you get an antibody like protein? And what if you get something, let's say 20 kD, 25 kD? So the minute the molecular weight is less, that means protein backbone size is less, number of charges is also less. So the overall energy, inherent energy that is inbuilt in that particular protein backbone will be less. So there, as a user, you have the flexibility. You can either acquire it at 15,000 or you can acquire it at 240,000. No harm in it. So by doing so, for let's say 20 kD, 25 kilodalton protein or 30 kilodalton protein, you will end up getting isotopically resolved molecular weight. Right? I do have a slide, I will show you these things. What is isoform and what are isotopes? So let me explain some small molecules. Let's say you were trying to acquire some kind of a small molecule. Right? It could be a drug molecule or it could be a impurity agent or impurity anything. So in such cases, the sort of resolution purely depends on the experimental objective. Now, what do I mean by objective? Let's say you want to do screening. Simply want to identify all of the small molecules, all of the metabolites, so-called metabolomics. Right? In such case, metabolomics are a bit notorious, analytically challenging. They tend to co-elute even though you end up designing a very good chromatographic gradient. Still they tend to co-elute. In such cases, it is always good to have high resolution data. So at the MS1 level, you can do high resolution. But what if you want to scan it very fast? So in that case, you need to reduce the resolution so that your scan speed is higher and you are able to get as much as data point as possible. Right? So that kind of a data, it can be used for qualitative and to some extent quantitation also. Now going to quantitation. If you are trying to selectively quantitate that particular small molecule in a given sample, then essentially it has to be low resolution, or in certain cases, if there are near isobaric interferences, you can consider it to avoid high resolution. So low resolution means much faster, high resolution means relatively slower. Low resolution means much more data points, high resolution means much less data points. This is where, as a scientist, you need to think how many data points you need across a given chromatographic peak. I need at least 10 to 12 data points. I do have a calculation, right? So it is that slide. I need at least 10 to 12 data points. Then, okay, let me do it at low resolution. I'm okay with 5 to 8 data points. Then, okay, I'll get good resolution. At the same time, expected data points. So this is how you need to understand this particular logic and extrapolate it when you are designing an experiment. Fine. So now let's go to the next slide. Now, in this particular session, I will give you some of the tips and tricks of how to set up the methods, right? And so-called analytical method optimization. After this thing, I will show you the routine thing. MS1, MSMS, proteomics, metabolomics. I will show you all the results and how the experiment looks like, fine? Right. Let's start with the definition. HRMS, high resolution, accurate mass spectrometry, fine? Full MS, nothing but MS1. It collects the mass range without any fragmentation. That's what it's called full MS. In simpler words, we call it intact mass. It's just profiling. Second thing, selected ion monitoring. You are acquiring a very narrow mass range around specific MIC value or values. I mean, multiple MICs can be monitored one after the other or simultaneously. Right? That is called SIP. This is essentially being done for targeted quantitation at MS1 level. Right? The next thing is TMS2. Targeted MSMS. Right? You are selecting a specific MIC with the quadrupoles and then you are using the fragmentation. So it generates MSMS, MS2 data. So here you are trying to selectively quantify the molecule based on the fragment, but not just based on the MS1. This could be done for fragments or for analytes which carry identical mass. Let's say you have two masses which are near isobaric or which are identical. Those kind of masses can only be separated, resolved at MSMS level. So that is where MS2, TMS2 level quantitation comes in very handy. Finally, DDMS2, data dependent MSMS. So this is nothing but triggering an MS2 event for all of the identifiable, visualizable MS1 data by the instrument. So that is what we use it in proteomics. That is what we use it in metabolomics. For all non-targeted global workflows, we use DDMS2, which will give you list of proteins, list of metabolites, list of small molecules, whatever it is. This can also be done in a targeted fashion, wherein you are including selected list of masses, MIC values, and the instrument will be dictated R fragment, what is the mass value. So that is called targeted DDMS. That is also possible. Okay. So now let's go to the next slide. Some little bit of definition about the so-called what is absolute normalized. Logic is that absolute T, equivalent energy, means the acceleration of the selected MIC into a neutral gas molecule to form fragmentation. Right? So you are giving, let's say, 20 electron volts. 20 electron volt is being applied onto the molecule without any scaling up or scaling down, based on the molecular characteristics. What is normalized? Normalized is similar to absolute. Only difference is it is scaled to the m by the uncharted. So it is this is just molecule. Whereas this is what? It's based on the molecular mass and the charge. So here you are not disciplining it, defining it. Here you are allowing the instrument to discipline it further. So lower FIG uses lower effective collision energy. Higher charge state it needs or induces a lower effective collision energy. So based on the charge state and FIG, the collision energy will be scaled up or scaled down. Right? So from my point of view, to begin with, for beginners, I always recommend them to use normalized collision energy. Once you get the expertise, then probably you can experiment about the absolute. How does the data, same molecule look like when you're doing normalized and when you're using absolute. Normalized always gives you much better fragment-rich data. And then the next thing is FWHM is something that is known full width at half max. So the width of a peak measured at half the peak height. Right? This is chromatographic parameter. You also end up seeing all these things in QLCs and UPLCs. The next thing is AF, all ion fragmentation. Whatever species that enters into the instrument, all of it will be fragmented without any definition. Without any definition from the user or to the instrument. That's called all ion fragmentation. This is only useful if you want to generate a very large spectral library. This will be very rarely used, so don't worry about it. TA, data independent acquisition. The fragmenting all ions passing through a roving M by Z vector. There is little bit of definition is there, discipline is there. So this you can actually use it to develop a spectral library or spectral library based protein or metabolite identification. So this is what in other instruments they call SPAN. We call it DAA, data independent acquisition. Both of them. So data dependent is identification based on a FASTA database. Identification based on a small molecule repository library. Right? Let's, for example, proteins, you must be using Unipron, NCBA. For small molecules, you must be using PubChem, HMDB. Similarly, in DAA, instead of using a FASTA sequence database, instead of using a publicly available repository, you are developing an experimentally validated spectral library based on data-dependent approach, and that particular library will be used in the place of FASTA database to get the identification. What is the advantage? The advantage is you end up getting more IDs. That's the advantage of having DAA over DTA. But for routine applications, I always strongly recommend you guys to use data-dependent MSMS or data-dependent approach. Right. So let's go to the next thing. So some of the other important parameters. But in this particular slide, I'm going to talk about microscans. That's also an important thing. Suppose say, what does this microscan mean? Number of scans that is being generated, acquired by the instrument to generate one master scan. Suppose if we set the value as 1, that means 1 microscan has been acquired to generate 1 master scan. The minute you make it 2, 5, 10, that means 10 microscans are being generated, acquired to get 1 master scan. What is the advantage? What is the disadvantage? For let's say small molecules, peptides, you need only 1 microscan. You don't have to average them more than 1 or 2. That is will give you isotopically resolved species. But for proteins like antibodies, you need to average them for 5 microscans, 10 microscans. That would give you much better baseline resolved spectrum. So that is where you need to choose microscans. The microscan choice purely depends on the analyte and the experiment. Bottom line is, for proteomics experiment, use 1 microscan, MS1, and 1 microscan, MSMS. For metabolomics, same logic, 1 microscan, MS1, and 1 microscan for MSMS. In cases, if you suspect that particular molecule, that particular analyte is very, very low abundance, but for some reason you need to get very good MS2 quality, MSMS quality, then you may consider averaging it out. Let's say you can consider changing it from 1 to 2, or to 3, or even to 5. But that is going to reduce the scan speed. That is what is being mentioned here. If you could see here, with microscan 1 at 60,000 resolution, the instrument can acquire 6 spectra per second. However, with microscans too, the same instrument can appear only in 3 spectra. So your speed is reduced by 50%. 6 hertz, 3 hertz. So now you need to take a call. Do you need more spectra per second or do you need more data points per second? So more spectra per second, that will be helpful for quantitation. Less spectra per second is good for qualitative application. Your spectra will look very good. But when you zoom it, when you try to integrate it, the number of data points across the spectra on a Gaussian plot, it will be much lesser. So for quantitation, you need to have more data points. For qualitative applications, it is okay to have even less data points, as simple as that. Right? So now let's go to the next slide. All right. So I was telling you about AGC, right? So the very important and exclusive parameter for any kind of a tracking instrument, especially orbiter. You will come across this term very often if you go through some literature survey in all of the orbiter platforms, orbiter published literature. What is AGC? Automated gain control. That's what AGC means. Now, what are we trying to do? We are trying to balance out the amount of ion population entering to the instrument. And we are trying to balance out the time that is being invested to accumulate the ion population. Now, why are we doing it? If the amount of ion injected into the instrument is very high, if it is too high, the density of the charges per unit area will be too large. This is called space charging capacity. And if the ion count is too low, there will be signal instability issues from spectrum to spectrum, intra-spectrum variations. That will compromise your mass accuracy. So this is where you need to balance it out. Make sure you inject into optimum amount of ion population. That so-called optimum amount of ion population measurement is nothing but AGC, automated gain control. Next, coming to the time factor. Okay, you know some more for some reason 1 lakh, 2 lakhs, 10,000, 20,000. This is the AGC value. You know it for some reason, some publication or for some kind of a math calculation. Next important is time, ID, injection time, fill time. So that is what is being done by ICD, independent charge vector. So it will measure the ion flux to determine the ion fill time. So this has been essentially achieved to get maximum intraspectral dynamic range and sensitivity. At the same time, it will avoid direct saturation or the so-called space charge effect. So all these things will give you better resolution, better mass accuracy, thereby authentic identification. I'm sure this particular slide, it sounds too technical, too scientific. I'll try to explain in much simpler words the subsequent slide. Just bear with me for 2 more slides. I have an example slide where I will explain you why it is important to control ion population injection and the time. We should not inject more, we should not inject less. That is called ion injection conversion. The next thing is time. We should not inject for more time, we should not inject for less time. Right? So now let's begin with this ICD. This so-called ICD, independent charge vector. This is used to improve the control of ion fill time. How do we control it? Through this particular parameter. So if you set it to 6, what does it mean? It means the instrument will generate a free scan every 6 seconds. Or every 6 seconds calculate the ion fill ratio, ion filling time. So this is very important. And this is being done by this particular component, independent charge vector. This will improve to control the ion fill inside the screen time. Right? Right. This is how the function, actually the hardware function. So the ICD has something called split length. So the split length has 3 modes. So it can either dictate the ion to the 3 trap and ion routing multipole, or it can divert it to ICD, or it can simply close it. Now you can imagine this is simply the MS1 run or FSMS run. This is the pre-scan. So 6 seconds is done, 6th second is doing ICD. Again it will repeat. So every time it will repeat, and if it is required, it will close it. So by closing it, you make sure you are injecting only the required amount of ion population for the required amount of time. Thereby, you are going to avoid space charging effect, delta saturation, so on and so forth. Now, I will explain you what it is, what is so-called space charging, delta saturation, coalescence, what is it, what does it look like, how does it look like. I will tell you the next slide. So, all these things have been achieved by a process called program. The first orbital signal adjustment. So let us not get into it, it will add a little bit of more complexity. I will quickly go to the slide wherein I will explain you about the AGC, right? The dynamic AGC and so-called AGC functions. Right. If you could see this particular slide, slide 25, this is nothing but MRFing. This is one of your calibrant. Alright. Now let us try to zoom in this particular isotope, A2. First isotope, second and third, right? So I am zooming in this one. Here I am getting some sort of a shoulder peak, a split peak. So is it because of the instrument artifact? Is it because of a near isobaric interference? Is it a background? What is it? Nobody knows. Now the minute you increase with much better, higher resolution, you are now able to separate it. Okay, this is my actual isotope, whereas this is something else. So you can get the composition also. So what is it? It could be simply the isotopic counterpart, or it could be another species. So this level of clarity is required even at the second or third isotope level. So that as a user, you will be able to judge, is it the isotopic counterpart of the same analyte, or is it something else, some other intervention. Right? Just compare this and this. Now I will explain you how this is being attained, or how AGC and ID time helps us to attain this kind of a data. It is not only mass resolution, it is mass resolution combined with AGC and ID time. Just try to have a critical look at this data from left to right. Very good data, okay kind of a data, not really good, bad data. Right? What is the difference? Try to look at the top panel. 5 milliseconds, 75 milliseconds, 100 milliseconds, 200 milliseconds. Now come to the bottom. 200,000, 285, 1,60,000, or in fact 16 lakhs, 19 lakhs, 30 lakhs. Right? So what is the difference here? The actual difference is time and AGC value. The resolution is same. The instrument is being acquired with the same resolution parameters, but with different AGC and fill time or the injection time. That's what you will see in the pressure interface ID time. One you call AGC. AGC is this guy, the bottom number, right? And the other one is IT, the top number. Now by feeding the right value, AGC and ID time, you are avoiding warping or peak splitting. Right? That's the bottom line. AGC is used to improve resolution and thereby mass accuracy. Just look at the mass accuracy. This is very accurate. And this is okay, but still you see a peak splitting or a shorter peak. This is not good. This is ambiguous. You will not end up concluding anything. And this is definitely you should not use it. One thing is the error is more. The other one is actually a peak is nothing. So this is the actual benefit, or in other words, the so-called overfilling, the so-called delta saturation, so-called coalescence. Here it is optimally filled, optimally acquired. Here, no, it is not. This is the logic behind the so-called space charge effect, or the coalescence, or the so-called peak merging. Right? This is where AGC and ID time is equally important, apart from resolution, mass range, collision value, all those things. Alright. So, the other important parameter is maximum ID time, maximum injection time. Alright. So, if you could see here, simply the maximum time that the system will allow the ions to fill into the ion routing multipole while trying to select the AGC target before passing it to the T trap. So it is essentially the same process that I had explained to you in the earlier slide. How much time we are investing, right? So you can either set it auto. Auto is for beginners. Once you know you are habituated, you have got the expertise, then you can take it to custom, and you can even fill the values. Let's say 50 milliseconds, 100 milliseconds, like that, right? Provided that it should not overfill, right? Make sure you are very sure about AGC value and injection time value. If you are not sure, leave it at standard, leave it at auto. If you are sure, then you can make it custom. Click on it, custom will come. Click on this, custom will come. You can fit the value. That's the logic, right? And this is what auto, custom, dynamic mode means. If you could see, you click on here, all the three options will be there: auto, custom, and dynamic. So accordingly, you will be able to set it. Let's say for full MS, the instrument sets the value according to the transient clearness. For example, 247 milliseconds for 1,20,000 resolution. It is automatically set. It is auto. For some reason, you want to acquire 120K resolution for much longer time, then click custom. That's the logic, right? So similarly, that is what is custom. You can see the maximum value that can be set is 1000 milliseconds, right? And dynamic, it calculates the maximum ID based on the LC frequency divided by the desired number of minimum points across the field. So you need to define these things. Specifically, this is required when you are trying to design quantitative experiment. So this is how the user has to choose whether it is auto, custom, dynamic. In much simpler words, auto is for beginners. Don't change it. Custom, once you understand the logic behind AGC and IT value, IT time. Or in cases wherein if you want to reproduce the published data, the data parameters are already there. If you want to reproduce it, yes, we just need to read the paper, get those parameters, use custom, and paste those parameters. Dynamic is good for optimizing experiments, specifically quantitative experiments, wherein you will be able to even set the desired number of minimum points across one given field. This is the logic, right? All right, resolution. Yeah, this is an important thing because the logic when to use high resolution, when to use low resolution. I'll tell you in much simpler way. Low resolution will fit for all the molecules. Whether it is small molecules or big molecules like antibody, it will fit everybody. In low resolution, as the name suggests, mass accuracy will be low. Isotopic resolution may or may not be there. That said, when would you move from low to high? If you want isotopic resolution, if you want very high mass accuracy, if you want to separate a molecule from near isobaric interferences, background molecules, then go to high resolution. When one should not go to high resolution, if your molecular weight is very high, 150 kilodaltons, 200 kilodaltons, no point in going very high resolution because that molecule is very big. It will inherit so much of charges that if you make the molecule to move around the electrode for longer time, higher resolution, right? If you make it to move for longer time, they will tend to undergo transient decay during the movement. Therefore, if the molecular weight is very high, don't go for high resolution. Very high means 70 kilodaltons, 100 kilodaltons, 150 kilodaltons. If it is low, you don't have to worry about the resolution. Right? You can play with any other resolution parameter. Low means I am saying less than 20 kilodaltons. 20 keda, 15 keda, 10 keda, 50 daltons, 1000 daltons. All these are all very low. 100 daltons, these are all low. For all the small molecule applications, go for high resolution. No harm in it. I mean, you can either go for 60,000 resolution or 1,20,000 resolution. And for your curiosity, if you want to go, you can go even for 2,40,000. Right? But if the molecule is high in the sense greater than 50 kilodaltons, then you need to be cautious about the resolution set parameter. Fine. That's the bottom line. Now let's go to the next slide. What does that so-called high, low would translate into? Let me give you a simple example. If you could see here, this particular graph, right? So I'm trying to zoom in this particular region, 5.8 to 5.9 minutes. X-axis is minutes. Y-axis, let's say it is some sort of carbon intensity. Fine, let's not worry about that. So within 0.1 minutes, which means 6 seconds, which means 6,000 milliseconds. So in 6,000 milliseconds, so if you are acquiring at, let's say, 30,000 resolution, right? It will acquire approximately 72 spectra. In 6 seconds, it will acquire 72 spectra. If the set resolution is 30,000, right? Same sample, same time, 6,000 milliseconds. If you are going to set it at, let's say, 60,000 resolution, that means 160,000 milliseconds. So the same sample, it will only get acquired 36 spectra. The minute you increase it further, 18 spectra, 9 spectra. So these many spectra per 0.1 minute or per 6,000 milliseconds. So this is where you need to decide whether you need high resolution or low resolution. For quantitation, you need to balance out. Let's say that's what is written on the top panel. For quantitation, 10 to 15 data points is required. For cleaning, doesn't matter. 4 to 8 data points is also okay. So all your proteomics, metabolomics, all these things you can call them cleaning. Untargeted workflow, global workflow, it is all kind of cleaning. So for those things, you don't have to worry about the resolution. Even high resolution is okay. But for quantitation, you need to be very sure about the resolution. Okay, I need at least 10 to 15 data points per chromatographic peak. Then probably you cannot go beyond maybe say 30 or 60,000. So this is how you choose resolution. Fine. For both qualitative and quantitative experiments. Alright. So one other question that most people ask is, what are the data types that they need to choose? Is it profile or centroid? First I will show you what profile means, what centroid means, and then I will tell you where to put what. So now this is the profile of 161. The mass is 161 something. Profile means this is how the data actually looks at that particular analyte. This is what is profile means. 151.090 to 151.094. You get a perfect Gaussian. This is profile. Centroid, suppose you want to acquire this centroid at that particular base peak. Whenever you do a chromatography, right, it's going to tell you start diluting, gradually increase, reach the apex, and then gradually decrease. Right? So at the point which the sample elutes at the maximum, the apex region, that is where it's going to be very, very high accurate, right? That is what centroid is. So now, if you see here, I am trying to integrate it. Why do we integrate? Integration is to get the area under the curve or intensity, whatever field. So if you want to integrate, in other words, if you want to quantify, the choice of mode has to be profile. If you want high mass accurate data, the choice has to be centroid. Simply because of the reason, the data is stored with just a mass and an intensity for each M by C. Especially the most centroided base peak, that's it. So here if you see the mass accuracy will be fantastic, centroid. In profile, compared to centroid, it will be a little bit less. Let's say here you get 0.1 ppm, 0.2 ppm or less than 1 ppm. In profile you may get less than 5 ppm or less than 2 ppm. That is the logic. Now where to put what? For quantitation, profile. For qualitative, centroid. Right? So if you say, let's say, you are doing proteomic experiment, MS1 data, which means I need to collect the complete mass range, 350 to 2000 M by C. Low molecular weight peptide, high molecular weight peptide. In such cases, use profile mode. You do, once you collect the MS1 data, you are going to do MSMS. The MSMS is for each and every peak, selected peptide parent peak. There your MS2 fragment accuracy has to be very high. There you use centroid. Suppose if you set up the same experiment, but not for qualitative research, but for quantitation, you want to quantify selected list of peptides, selected list of small molecules, then you may have to consider keeping it as profile. So you will get much better peak shape, much better area under the curve. This is the logic, nothing else. Right? So we'll go to the next slide. One other important thing, advantage with this particular instrument is something called mild tapping. The logic is that I'll not spend too much time. But this so-called small molecules, whenever they enter into the instrument, they tend to undergo spontaneous dissociation without even the user applying any kind of a collision energy. So if you apply an energy and if they are getting fragmented, it is okay. That is part of the plan. That is an experiment. But some molecules, because of the fragile nature, due to the instrument characteristics, instrument features, it could be pressure, it could be inbuilt electrostatic field, or it could be any form of energy, they tend to undergo spontaneous dissociation. So that is what is being essentially avoided by so-called mild trapping. So if you could see, that is the graph here, right? Bar graph. X-axis is different, let's say, small molecules, phenylalanine, isoleucine, adenosine, glycodeoxyfolate. Y-axis is ratio of the fragment versus, by precursor ion. So if you could see, in normal pressure condition, it is fragmenting. Without applying any kind of a fragmentation energy, it is fragmenting automatically, spontaneously. That is slower. In mild trapping, where the pressure is regulated, this is non-regulated, blue color. Green is regulated. That's what we call mild trapping. So in mild trapping condition, the fragment ions are very, very less. That means spontaneous dissociation of the small molecule has been controlled. This is good when you are doing some kind of a small molecule or a metabolomic kind of an experiment. This is for your information. This is all that you need to do is just check it. In the instrument metadata page, there is an option where you can enable. Just check it, tick it, right? Enabling will enable mild trapping. If you don't tick it, if you don't check it, it is a normal pressurization. That's the logic. All right. Scan rate in TDMS to TMS2. I think this we had discussed already. Where you need to have factor of 5, factor of 10, factor of 15. This is the first thing that I explained to how to set the mass range, right? So let us skip this particular slide. So this particular slide shows the example. So what is the factor? 40 to 200, 40 to 200, 48 to 240. Lower mass range, higher mass range. First mass, last mass. So you can see mass range rise. 150 to 1500, 107 to 1600, 133 to 2000. So these things you can keep in mind. It will be easy for you to set up the experiment. Right. So this is nothing but the 5, 10, 15 role. To get the mass range. What if you unknowingly set it to a level that is beyond the instrument capability? In that case, it will show you an error. Yellow is okay. Ideally, it has to be white. If it is yellow, it's like above or below the recommended range. If it is red, it is definitely not recommended. That means you are violating the rule. So you will get this kind of a color. So immediately you need to apply the rule. Okay, supposed to be 100 to 1000. Whereas by mistake, I have made it 100 to 2000. So you need to change it. Similarly, you could see here 40 to 1000. No, sorry, that is not possible. 40 to 200. That is what is possible. So this is how you need to change it. And this is how the warning message looks like. Okay. This is absolutely not okay. Right? Alright, now let us go to the different modes of data acquisition, different experiments. So first is acquisition mode and the 3 principal components. These 3 are the very, very important components. Quadrupole, ion routing multipole, orbital. Of course, data is important, but then from a function perspective, these 3 are going to be there as a part of the experiment method setup. First is full MS, intact MS, positive delta monitoring. What we are going to do now, this is how you need to set it. You can see here, left hand side, bottom panel, full scan. You set this thing, the time, the gradient time, LC time, set the mass range, and the resolution that is required. So when you do it, it will start acquiring that particular mass range. That is called full MS, complete mass range. Let's say you are set to 10 to 1000. So it will start acquiring from 10 to 1000. That is called full MS. Now, This will acquire, much wider mass range. It will measure all the ions. That is the ultimate objective, full MS. Now, where does this full MS get employed? So it is essentially for, let's say, you want to do some kind of an intact mass of a protein. So from intact mass, you get the protein mass, molecular mass, and you also get some clue about the modifications. It could be PTMs, both acid modifications, it could be amino acid blocks, N-terminal excretions, truncations. All these clues you will be able to get when you measure the intact mass of a given molecule, of a given protein. Right? If you could see this particular slide 52, from top to bottom, intact mass of a peptide, low molecular weight protein, and high molecular weight, this is the antibody. Right? As you see this is the same data I'm zooming in. Earlier data was the complete data. Next data is it is zoomed in. You can see this isotopically resolved. These are isotopes. And this is the isoform. These are isotopes, I mean C12, C13, N15, O18. And these are nothing but different. It could be either amino acid or it could be different glycan isoforms. In this case of antibody, it is glycan isoforms. Now let's go to the next slide. Where does these things come? It is very handy. For example, in biosimilars, like in morning session, doctor has pointed about biosimilar analysis, right? Categorization. So I'm just trying to put one example data. Top one, T-glycosylated map. Bottom one, glycosylated map. Now let us try to zoom in one of the peaks. You can see here, glycans are removed. Glycans are intact. Where will this kind of an experiment help? This kind of an experiment will help the scientist to differentiate between glycosylation and glycation. Even after deglycosylating the protein, you still see a second peak. So the glycans are supposed to be removed. Yes, they are removed. What is left? This may not be a enzyme-driven glycosylation, covalent bond. Probably this is the glycation. So these kind of experiments can be designed using the intact mass, and this is how the data would look like. This is for an antibody molecule. Right? Now, I'll show you about the data for isotopic and isoformic resolution. Top panel, 1,40,000, 2,80,000 resolution. Bottom panel is approximately 15,000, 17,000 resolution. Now we will try to zoom in one of the peaks again. You see here, this is the isotopically resolved intact protein. Molecular weight is less than 20 kilodalton. This is isoformically resolved intact protein. Molecular weight is 150 kilodalton. This is antibody, and this is nothing but the non-pegylated silk acid, ETSF. Granulocyte polycumulating factor. I'm sure some of you must have read about it. The therapeutic protein. Let's go to the next slide. In this particular slide, we are using the same intact mass data to comment on the glycan microheterogeneity. Both of them are antibodies. Top panel, bottom panel. Right? Both are antibodies. Both are IgG1. Only difference is glycan heterogeneity, glycan microheterogeneity. Now if you zoom it, you can see here 6 to 7 different glycan isoforms. Part 3 to 4 glycan isoforms. This is one other application. Right? Now let's go to the next slide. Right. If you could see here, these are 4 different, let's say, protein samples. What is the difference? Let's come from left to right and from top to bottom. Left, top panel. Protein with no modifications. Right. Top panel. Protein with greater than 5 modifications on the same site. Same amino acid site. Panel 3. It is protein with only one modification, but that one modification is spread across multiple sites. And panel D. It's one protein, different modifications on different sites. So this is the level of heterogeneity. No modification, 5 different modifications on one site, one modification on multiple sites, multiple modification on multiple sites. This is how the data looks like. So now if you go to the next slide, that is the raw data. The earlier slide was the raw data, raw spectrum. This is the deconvoluted data. Protein with no modification, same protein with one modification on multiple sites. One protein with 5 different modifications on the same site. Polydispersed, different modifications on different sites. This is how the deconvoluted data looks like. So this is the data in nutshell, intact mass, so-called MS1 in nutshell. So now you know how to set up what is MS1 and where to use MS1 from a protein perspective. Same logic can be applicable for small molecule also. I will quickly go through the slide. In small molecule, it is more about not just MS1, it is also about resolution. So what if a user has been asked to acquire a sample that contains, let's say, near isobaric interference or near isobaric analytes that are chromatographically co-eluting. So if you could see in this particular slide, we are trying to acquire arginine and N-acetyl ornithine, which is separated only at the second or the third decimal place. And fortunately or unfortunately, they are chromatographically co-eluting. In such case, this is how the spectra would look like if you acquired at 15,000 low resolution. Let us increase the resolution 30, 60, 1,20,000, finally 2,40,000. Different color code correspond to different resolution acquisition setup. So the minute you increase the resolution, we are able to separate near isobaric analytes. From a scientific standpoint, scientists they always claim that we do have very good chromatographic methods in place, wherein we will be able to chromatographically resolve near isobaric analytes. But what if it is not an analyte and if it is a background? That is what is being shown in the next slide, slide 63. The logic remains the same between earlier slide 62 and 63. The difference is that earlier slide it is near isobaric analytes. In the next slide, it is not an analyte, it is an isobaric background ion. So in this case, it is phthalate. Phthalate, which is near isobaric to ester ion. Again, the mass is only differing at the second or the third decimal place. So in this case, again, by acquiring the same sample at much higher resolution, we are able to separate the analyte of interest from a background interference. This is not as important when you are trying to set up a MS1 experiment for a small molecule application, right? And this is how the data would look like in reality. Bottom panel, low resolution, top panel, 1 lakh resolution. This is the logic, right? Now let's go to the next slide. Does it really get employed? Yes, it did. If you could see here, this is a representative list of drugs which is showing near isobaric masses. Differences at the second, third, fourth decimal place. If at all you encounter these kind of molecules to be analyzed in your lab, obviously mass resolution will come into very, very handy. That's why you have this kind of an instrument in your lab. Right? Alright, so now we have seen enough about MS1, qualitative experiment, intact mass experiment for proteins and small molecules. Next is targeted MS1. In much simpler words, selected ion monitoring. If you could see the left-hand side bottom panel, this is a SIM scan. These are the list of molecules. In full MS, you don't add the mass or the list of molecules. Whereas in SIM, you should add the list of molecules, specifically the mass. So the mass can be calculated based on the formula or it could be based on some kind of a literature reference. So what happens? These lists of masses will be selectively acquired at MS1 level. So this particular thing is being done so that you will be able to quantify it at MS1 level. I think just a minute. Oh, yeah. Now let's go to the next slide. How does it happen? This is how it happens. We are selecting only one particular mass range, and that is being allowed to pass through the quadrupole. Ion routing multipole helps you in accumulating it, normalizing, cooling down the ions, coming with different levels of energy. Finally, you are trying to acquire it, measure it using orbiter. So if you could see, try to correlate this animation, right? We are passing a narrow mass range. Try to have a look at this particular spectra in the bottom. You are accumulating it. The minute you are accumulating, you are getting this kind of intensity. You accumulate more. You accumulate more. Thereby, irrespective of the interferences, This is the actual abundance. Actual relative abundance. By using T-sim method, you have selectively isolated, selectively enriched this particular molecule. Thereby you will be able to get much better, much precise quantitation. This is the logic or difference between T-sim and MS1. You can simply imagine top one. This is MS1, bottom one, T-sim of this particular molecule. That's the logic. Alright. What do we actually gain? That's what I told you. We gain sensitivity. So if you could see this particular slide, this slide is all whatever logic that I explained in the earlier slide. This slide shows you in a figure format. Blue one, assume this is the actual sensitivity. Red one is T-sim. You are gaining sensitivity by almost 7 times. So this is the advantage of employing T-sim. Selective quantitation of a given molecule at MS1 level. As simple as that. Alright, now that we know how to do qualitative and quantitation at MS1 level, this particular slide is about quantitation at MS2, targeted MSMS. Logic is there. Instead of sim scan, you should select broad diameter scan, tabulate all the list of molecules and their mass based on their formula or based on the literature. So these molecules now will be fragmented. Right? The other thing is SRM. So SRM is nothing but selected reaction monitoring, wherein the difference between TMS2 and SRM is, in TMS2, you don't have to feed in the fragment ion mass. Whereas in SRM, you have to feed in the product ion mass. I would say TMS2 is a good starting point. In cases, if at all you come across a table, something called PRM, parallel reaction monitoring, that is nothing but TMS2. Suppose if you want to extrapolate SRM and MRM, again, those things can be done using TMS2. Only difference is, in MRM and SRM, they would have mentioned both parent ion mass and the fragment ion mass. Whereas here, you don't have to mention parent ion mass, it is not a must. Knowledge about parent mass is good. Knowledge about fragment ion mass is not required. As simple as that. Right, we'll go to the next slide. Yeah, this is the useful experiment. Full MS followed by DDMS, so data dependent MSMS. So this is how the metadata space looks like. It is more non-targeted, proteomics metabolomic application, wherein you select a mass range, measure the mass, and determine the MSMS of each of the measured mass in a sequential fashion. That's the logic. So it's not targeted, as I told you, step 1. Mass spec selects the mass range, measures the mass. This is MS1 data, profile mode data. Then select the ion, top end 12, top end 15, top end 20, based on intensity. And then perform MSMS. So this is what MSMS, DDMS is all about. Data dependent, MS1 data dependent MSMS. Now there is something called full MS, DDMS2 with inclusion list. What is, you want to select some, let's say there are some low abundant keys, which are very critical. They are of biological technical significance. It is not getting fragmented well. In full MS, DDMS2. In such cases, you use full MS followed by DDMS2 along with the inclusion list, targeted list. Therefore, in that particular thing, even irrespective of the abundance, those masses will be fragmented. This is one way of selectively enriching and identifying a low abundant T. So the logic remains the same. You do full MS, MS1 data, and then you based on the inclusion list, the data that you have fed into the instrument, the mass spec will select, in case if the list is there, if the mass is there, it will select it and it will fragment it. That's the logic. But in spite of doing this thing, if you are not getting good fragmentation, then the only way of doing it is we need to enrich that particular species and then do the analysis. Right? Now let's go to the next slide. Yeah, bottom-up proteomics, right? So the so-called DDMS2 approach, it has all been applied the so-called bottom-up proteomics. So in that particular thing, These are the different sort of bottom-up proteomics approaches. I'm sure you guys must be familiar, or else I'm sure you will be employing one of these techniques. 1D page, 2D page, fractionation followed by 2D page, or online, offline, 2D, 3D, LC-HRMS. These are the different sort of approaches that we employ to define the proteome of a given cell or a sample. This particular slide, it just gives you an example of one of what one can design, how to isolate and how to identify and analyze. This is data generation, data analysis workflow. Right. And this is a representative 2D gel, wherein you will be, in case if at all you are doing 2D page-based approach, you will get this kind of a jelly page, wherein you will be picking up each and every spot to identify the protein of interest. And this particular thing, slide 88, it is about simple 1D LC-HRMS then, wherein you take the sample of interest, digest using trypsin, desalt it, and inject it into the nano LC. This will give you the nano LC-MS run, wherein you will be able to get this kind of a list. So automatically you are able to identify all the available protein or the proteome component of that given sample. These things can be done using proteome discoverer. So these are some of the key things, like whenever we are doing with proteome identification. So one important thing is the length and breadth. I mean the number of unique proteins and the number of unique peptides per protein. That would be much better when you are doing the experiment using orbital. So from proteomic data, apart from protein ID, depending on the database information, whether the genome is annotated, whether the proteome reference map is available, whether the functional annotation is already done, depending on the annotation information, you will also be able to get information about the item form, PTM form, all those things. Right? Now let's go to the next slide. Same logic you can employ when you are doing comparative proteomics, 2D page-based approach, wherein you are running two different gels to compare two different stages. Let's say it is patent, healthy versus patent, control versus mutant, or disorder, some sort of a treatment. So these are all gel-based approaches, 1D page or 2D page. In this case, it's 2D page-based approach. So once you have the data, you will have these kind of analysis, wherein you will be able to pick up the spots, differentially express spots. So it is here, whereas it is not there in the control. So these sort of things you will be able to identify, thereby you will be able to say, okay, this particular protein is upregulated or downregulated in this particular condition. It could be disease condition, mutant, disorder, any kind of. So in case if you want to avoid the laborious dental-based thing, the alternative is obviously LC-HRMS label-based technique. One such technique is TMT, data mass tag, wherein you will be able to quantify proteins based on the data mass tag labels or I-tag labels. So this particular slide, it gives you an idea of what this is. Like say 10 different samples, isolated, digested, labeled using 10 different labels, pooled, and then run using the orbital mass spec. Then you will get these independent labels. The intensity of each of the labels corresponds to the intensity or the relative abundance of that particular peptide or protein in 10 different samples. As simple as that. So this is the logic behind label-based approach, label-based quantitative proteomic approach. This is how the data looks like. Again, same software, proteome discoverer, which can be used for both identification and quantitation. Quantitation in the sense, if you see the next slide, you are able to see the fold change. 127 is label number 1. 126 is another label. So 127N nitrogen isotope by 126. So that is 3-fold. So this particular protein is 3-fold upregulated. This is 9-fold upregulated, 6-fold. This is 0.5-fold, which means it is downregulated. So these sort of upregulation, downregulation can be automated. All these things are possible with the label-based quantitative approach. And this is label-free. What if you don't want to use the label? TMT labels or I-tag labels. In such case, area under the curve of a given protein or a peptide will be used to estimate the relative quantitative abundance of that particular peptide, thereby protein. So this is called label-free, without using any label. Only difference is that in label based, 10 samples can be analyzed simultaneously. You are labeling it, pooling it, and you are injecting in the instrument, let's say one or maybe thrice, triplicates. Whereas here, 10 samples need to be identified independently. So there, if you say it is 6 hours, 2 plus 2 plus 2, 3 injections, 2 hours each. That is for label based. So 10 samples will take 6 hours. Whereas here, the same 10 samples, it will take almost 10 times more. So each and every sample, let's say 10 samples. So it will be 20 hours. Triplicate, 20 into 3, 60 hours. So 6 hours versus 60 hours. 10 times more instrument time. This is the difference between label based and label free. Instrument time will be more. The other way around, label free is less cost. There is no cost. Label based, it involves the cost. So this is where you need to take a call. Alright, these are some of the tips whenever you are trying to do some kind of a label based approach. Right? So whenever you do label based, make sure you avoid interfering buffers. Most of the labels, whether it is ITRAC, TMP, these are all primary amine reactive N-hydroxysuccinamide esters. Having said that, make sure your buffer is free of any primary amine containing buffer constituent. For example, ammonium bicarbonate. Consider replacing tris or ammonium bicarbonate with triethyl ammonium bicarbonate, primary amine free buffer constituents. Make sure you avoid urea. In place of urea, you can use LCS. So these things need to be very critical when you are trying to design the experiment. Label free is again, it's based on MS1 precursor area. Right? This is based on reporter ion tag, reporter ion intensity or area. This is based on MS1 precursor area. MS2 resolution is very important when you are trying to design an experiment greater than TMK 6 plex. Like 10 plex, 7 plex, it means 6 samples together, 10 samples together, 11 samples together. So when you are doing it, MS2 resolution has to be much higher. So these things will come downstream. So as and when you guys are doing it, we will help you out with these things. So don't worry. This is just for your information. And in case if you are trying to do label-free approach, in that case, it is better that you spike the samples with internal standards. This is for normalizing data across data sets. In label-based, label is there, wherein you will be able to normalize based on some kind of a data point. Whereas in label-free, nothing is there, apart from samples. Therefore, it's always better to spike a known level of internal standard. For human protein, spike non-human protein. For plant protein, spike it non-plant protein. That is how the logic. So this is a summary. So the extent of proteome coverage, it depends on the concentration and fractionation strategies. So individual protein sequence coverage, it depends on the proteotypic nature. That is why if you see, different proteins will give different kind of sequence coverage. It all depends on the proteotypic nature. What is the kind of amenable peptides that protein is able to generate upon trypsin digestion. Right? So if at all you are trying to do PTMs and cloning, yes, you can do it without enrichment. Without enrichment, it will be giving you a clue. If you want to get a complete idea, it is always better that you enrich it and then do it. For whenever you are trying to do plan any kind of protein characterization activity, the purity, homogeneity of the sample is a must. Make sure the protein is devoid of any other proteinaceous impurities or any other non-proteinaceous impurities also. All of those things are going to interfere with your analysis, characterization aspect. For label-based strategy, as I told you, choice of buffer is very, very critical. And for label-free, protein quantitation is critical. Therefore, internal standard, spiking it with the internal standard is beneficial. I'm not saying it is mandatory. That is a statistical way of doing it also, but it's always better to spike it so that you are trying to control it technically and statistically. Whatever you do, experimental design and data analysis is the key. So it should be very critical whenever you are going to design an experiment. So these things will train you gradually, so don't worry on these particular things, right? Alright, so we have talked so much about proteomics, I thought I'll at least give you a snapshot about the metabolomics. Logically, both are same, proteomics and metabolomics. It is just that technically, the way you extract the samples, the chart of chromatography, for example, proteomics you must be using nano-LC columns. Metabolomics you will be using UHPLC along with UHPLC columns. Here in proteomics you will use aqueous buffers, metabolomics you use most of organic solvents. So those things changes. Then all the other things remain the same. Right? You can also do label-free quantitation in metabolomics also. So this is how the overall workflow looks like. Now let's go to the next slide. This is the omics in nutshell. So from your perspective, from master perspective, you can do proteomics as well as metabolomics. So that is how mass spectrometry will really help you in characterizing, analyzing. It could be a protein involved in fundamental research, or it could be a protein of pharmaceutical value or biopharmaceutical value. It could be any small molecule, whatever it is. This is how it can be used using. It can be done using the mass spec as a technique. So this is about all ion fragmentation. I think we can skip these things because these things you will be using it only in the very advanced stage, but all you need it. So the bottom line is that these are the different experiments or the methods that can be set. Full MS, DDMS to target enzyme, PRM, DIA, and where it is being employed. Full MS for generating the empirical formula, intact mass. Full MS, DDMS2 for library searchable, I mean proteomics, metabolomics. Targeted still for quantitation, MS1 based. PRM, parallel reaction monitoring, or TMS2, that is for quantitation. And DAA, it is for MSA, library generation. So this is the overall nutshell, all the methods in nutshell, and their corresponding experiments or the attainable result, right? And just to conclude, what this particular instrument can deliver and what it can translate into. This particular instrument, it can deliver very high mass accuracy, and that would translate into high accurate, I mean authentic and ambiguous identifications. It can also deliver very high resolution, which means you will be able to get much better coverage. It could be protein coverage or proteome sequence coverage. It can also be used for getting very high sensitivity and detection limit as well as dynamic range, both interscan and intrascan. These three parameters put together, it will help you to design very good quantitative experiment. And the possibility of hybrid analysis, I mean quadrupole and orbital, it will help the users to develop design multiple workflows. That's what we saw it in the earlier slide. So with this, I'd like to summarize. This so-called orbital is undoubtedly one of the major scientific innovations. It can be used for both in-depth analysis and specification of both small molecules as well as complex biomolecules and protein therapeutics. This instrument can deliver very high mass accuracy and resolution at both MS1 and MS2 levels. That is what is very important. This in turn will translate into unambiguous identification and calculation of analytically challenging molecules. In order to qualitative aspects, it is also being regularly employed for quantitative workflows. So, with this, these are some of the snapshots. If you could see, this is one of the recently published methods by USFDA, wherein they are trying to quantify the nitrosamine, zero toxic impurity in the antidote drug substance. And this was done in the benchtop orbitrap platform. And these are some of the scientific publications. The earlier thing was for industry, and this one is for fundamental research. This is one of the couple of scientific publications wherein both the groups, they have employed orbitrap based instruments to elucidate, to completely map the human proteome. So with this, I would like to conclude. If there are any queries, I will be happy to answer.
Thank you, Dr. Your talk was very detailed and informative. Most of the interpretation for the instrument things you have covered, and already we are off known, but still your talk is related as any more. Actually, we want to have lots of 5 minutes because, as I discussed with you, and some of our students' data is ready, so you can look at that and for interpretation, or you can answer the queries.
Yeah, sure. So maybe we can, now I think it is 4 o'clock. We can again join back at maybe 4:05 or 4:10.
Okay, fine. Meantime, we expect Dr. Balaban also will join.
Sure.
Because all the scholars like from particular department and those who unlike your sample, you be reading the data, whatever the screenshot or whatever the case for the asking questions or interpreting your data, etc., whatever. Do not leave the room, be in the room for another 5 minutes.
Roger తక్కువ అవుతుంది అడుగులో ఉంచుకోండి ఈ టైప్ చూసుకోవాలి కొంచెం better already something yeah, then the non-time for vitamins, vitamins, ఎంత పెట్టాలి కొత్త సాంపుల్ అడుగుతారు వన్ టైం ఎంత పెట్టాలి కేజీ సాంపుల్స్ మాకు సంబంధం తెలియదు కదా